In last video, we showed you the definition of the decision boundary, which is a linear or hyperplane. And in this video, I'll give you one short example. So, which is called the centroid method. Suppose we have some scatter plot. And we have some observations. Let's use different color. And maybe we give a dot here. And we choose different color here. Maybe we give a dot close to this class. Centroid method means the first step is to find, step 1, find mu c and mu x. So which is mean of all points in class C. Okay, and mu x denotes the mean of all the points not in class C. Okay, for example, suppose since the average of the orange dot, the average is somewhere here, say. Okay, and the average, so this is so mu c is a 2D vector in this example, mu c, and probably mu x is in here, so mu x is also a 2D vector. Okay, then we have a decision function. Is fx equals to mu c minus mu x. Okay, mu c minus mu x represents a vector pointing from this mu c to mu x. Okay, and multiply by x, dot product with x. This x is also 2D vector minus mu c minus mu x. Multiply mu dot product with mu c plus mu x divided by 2. Okay, so this is our classifier. So we can calculate for each point, we plug that point to this function. If this function give, so this is our one possible decision function. So let's see how this function is derived. Remember, in this class we talk about the linear case, the very simple case. So fx is a w vector, is a weight, dot product is x plus a scalar alpha. Okay, and the decision boundary is denoted by all the points on x plane, on the feature plane, such that W multiply x equals to negative alpha. So for somehow we need to solve. W vector and this scalar alpha. Okay. And based on the theorem we just introduced to you, this theorem 2. So for every weight vector, this weight dot product with this y minus x for the 2 points on the decision boundary should be perpendicular, right? So let's come back to our. So for this classifier, so this is our W weight matrix. So this means a vector pointing from this point to this point, and okay, so this mu c minus mu x is our normal vector, and we want our decision boundary should be perpendicular to this normal vector. So decision boundary should be either here or here or here or here. Okay. But the more mixed the point make more sense would be the center point. So where is this center point? If you remember, if you have 2 points, the center one will be the summation of the 2 coordinates divided by 2. So the center point will be mu c plus mu x over 2. Okay, and so we can plug in this point to this linear decision function. So we have the mu c minus mu x dot product with half mu c plus mu x plus alpha should give us equal to 0, because we know we want this point to be on our decision boundary, so we can solve our alpha. So this implies our alpha equals to negative mu c minus mu x multiply mu c plus mu x divided by 2. Okay, so this is how we get alpha. So this is a decision function based on the center of each class. So in other words, it's a line goes through the central point. So this is our decision boundary H. Okay. So this is just a simple example. And then next, we're gonna introduce, for more general case, how do we find this W and this alpha. So that's maybe the first algorithm we introduce in this class. It's called a perceptron theorem algorithm. Perceptron algorithm is given by the Frank Rosenblatt in 1957. Okay. So next we're gonna introduce what this algorithm is, and in your first homework, you will have the opportunity to implement this algorithm on Python. Okay, so consider sample points. So suppose we have the x1, xn is our training data set. Okay, and we have labels on the training too for each data. So yi will equals to 1 or -1 if xi belongs to this class C. If xi does not belong to class C. You can think of this example as the example we introduced at the beginning of the class. You can think of this each x represents a two-dimensional vector, income and age. And for each data point in our training data set, we have label as a reliable borrower or the defaulted borrower. Okay. So we just give a name. Reliable borrower we give 1, and the defaulted one we give -1. So now we need to give an algorithm how to solve this W and the alpha. Okay. So first, we assume alpha equal to 0. So in other words, we want our decision boundary cross 0. Cross origin. Okay, and later on we're gonna generalize. We want to find the W given the alpha, because you remember alpha just tells you the shift on the, because alpha controls the y-intercept. So if you give different alpha, you're gonna have the decision boundary, linear decision boundary with different at different location, but the slope will be same. Slope will be same. So now let's first simplify our problem to the case where the alpha equal to 0, and later on we're gonna introduce the method to solve for alpha 2. So the goal here is find that normal vector W weight such that xi inner product with W is greater than equals to 0 if yi equals to 1, and the xi inner product with W less than 0 if yi is labeled negative, defaulted one. Actually, this two condition can be written as the one condition. So, which means this xi times dot product with W has the same sign as yi. So if we have that in mind, we can combine these two conditions into one. So it's xi. Sorry, I need to use a capital one. Xi dot product with yi with wi, sorry, with W, and the scalar multiply yi is always greater than equal to 0. So which means these two quantity have same sign. And we need to solve this W by some solved problem by optimization. But if you want to solve by optimization, we need to have some loss. So we can define some loss function. So we can define the loss function here is LZ with yi. So they both are scalars. Okay, equals to, if it's correctly classified, so which means zi and yi has the same sign, greater than or equal 0, we don't give penalty. Okay, otherwise if zi minus yi is less than 0, we give penalty negative yi zi. So this is our loss function, and now we just need to solve this omega by many. So this is just 1 point, right? This is 1 point. So, and we can based on this 1 point loss function, we can define our risk function. Risk function. So risk function here is just r omega. So we need to, for each given omega, we want to average the loss. Average means we have n data points. We divide by n, and the summation the loss on each point xi, inner product with omega wi. Okay, so I from 1 to n. So actually this is just 1 over n summation I from 1 to n. Remember our loss is just either 0 or negative yiz, negative this one times, so another way to write down this is just negative yi scalar multiply xi. Xi is a 2D vector, and a dot product with omega w. And for all the points that misclassified, so where V is the set of indices I, for which they have opposite sign, yi multiply xi. This is scalar multiply, this is vector multiply, dot product, which is has negative sign. Okay, so now based on this risk function, we minimize this risk function, we can get a minimizer. Minimizer is the one we are looking for. Okay, actually we can plot this risk function. So actually so this is the loss function with respect to lambda omega. So actually there are many so this is a minimizer. This is a region that minimizes this loss function. So any points in this region could be a solution for our classifier. Okay, next lecture I will give you more details about the perceptron algorithm.